So our final lesson out of chapter 3 is on something called logarithmic differentiation. And it's the final skill that you need to be able to take the derivative of the last category of function that we haven't seen yet. All right, so we've got one more category of function. We've done trigs and inverse trigs. We've done rationals. We've done square roots, and we've done power functions. We did exponentials and logs, and there's one final category. All right, so let's look at these things. Now, you saw a slide like this earlier. Okay, what rule do we use to find the derivative of the first one? Constant rule. Why? Both parts of it, both the base and the power, are a constant, and so that's a constant rule. Nothing about it is variable. Okay. All right, the next one, I have one part that's variable and one part that's constant. Based on where they are, what rule do I use there? Power rule. Okay, one part of it is variable, one part of it's a constant. Okay, the third one, again, one part is variable, one part is constant, but because of where those are ordered, what rule will I use there? Exponential rule. What makes it an exponential? The 4. So the last combination is the bottom one, where nothing about it is constant. Okay, where the base is a variable and the power is a variable and there is nothing constant at all. Okay, so there's no rule, it's just a technique. Same like we learned earlier, we learned a technique of implicit differentiation. It wasn't a rule necessarily, it was a technique that we applied to things that failed the vertical line test. All right, so this is the last one. It's a technique that you're going to use when nothing about your problem is constant. And this is called logarithmic differentiation. Now, the names of these techniques give you the first step. Okay, so for example, implicit differentiation. The word implicit means that there are parentheses that are implied somewhere. So your first step is always put the implicit parentheses in and then apply the rules. The way this is ordered, logarithmic differentiation, means the first thing you're going to do is a logarithm. And then after that, you're going to do all the rules that you had previously used. So it's a technique, and it indicates the order in which you do things. Just like we name things point slope. Why? Because you need to find the point. It's the order in which you do things. Okay, so just keep in mind this is what we're going to do first. Yes. All right. So it is the process called logarithmic differentiation. It is a technique that allows us to simplify a logarithm process. It starts out looking messy, and then it's like all of a sudden, whoosh, everything simplifies, and you have a very simple answer at the end. And you would use it in a couple specific situations. All right, where nothing is constant. That's the first situation. Sometimes we call that super exponentials. Like we have, I call it super foil. Whoops, I can't spell. Okay, a super exponential where nothing is constant. The base has a variable, the power has a variable, there's no constants altogether. That's the most obvious one where you would use super exponential. The second one is an alternate to the quotient rule if the quotient rule is going to be really messy. And we'll try one of those too. So if you see one and you're looking at it and you're like, oh, the quotient rule is going to be horrific. I'm going to be squaring this massive thing and subtracting. And logarithmic differentiation is an alternate to that, which can tend to be cleaner. All right, so let's try this out. Okay, this is an example of one of those quote-unquote super exponentials because nothing about it is constant. X is a variable, cosine x is a variable. Everything about this is variables. Okay, so we apply logarithmic differentiation, which means we introduce a logarithm into both sides of this problem. What's our favorite logarithm? Great. All right, so we're going to apply the natural log. And if you do it, so we're going to introduce ln. So I'm going to put an ln around the y. But what you do to one side, you have to do to the other. So I'm going to also introduce the ln around the x to the cos x. And I use parentheses to do that. So we introduce an ln on both sides. Don't forget that. Okay, this is algebraic. It's an algebraic technique. In algebra, we're allowed to do things on both sides. That brings up another algebraic technique that is unique to logarithms. Yes, bring the cosine to the front. All right, that is an algebraic technique that would come down. So then the left side still is ln y, but the right side has the cosine of x in front of the ln of x. And what's the implied relationship between the two of those? Multiplication. So now, what rule can I use to find my derivative? So now you're ready for the differentiation part. So introduce the ln first, and then our second step is to apply the appropriate derivative rules, which is why we just practiced which derivative rules are appropriate in each situation. All right, so now we're ready to apply the derivative rules. So what rule do I need on the y side of the problem? Logarithm rule, right? And how do I find the derivative of a logarithm? 1 over. 1 over what?
1 over
Y. And what else? Natural log of e. And what else? Okay, dy dx.
Oh, I see.
Okay, the derivative of y is dy dx. It's not 1 like it was before. Okay, what rule do I need on the x side of the problem? The product rule. Okay, so what should I start with when I do the product rule? Natural log of x times negative sine x. What follows after that? Plus cosine of x.
1 over x.
1 over x, ln e, and then dx dx, right? Instead of dy dx, this time it's dx dx, but a couple of those things are 1. Okay, we know that natural log of e is 1, and the dx dx is going to be 1. Okay, and the ln e on the other side is 1. Yes, yes. All right, so just to simplify what we have 1 over y times dy dx. And then the other side we've got, let me see, I'll lead with negative, it doesn't really matter, negative ln x sine x, and then maybe plus, and what would the numerator be? Cosine x on the top and x on the bottom.
And then times
Okay.
y.
Yeah, and what am I trying to find? Go back to the original problem, find what?
The dy dx.
Right, dy dx, find dy dx, and it's like, oh, all right, I found it. dy dx is right here, except I need to get rid of this.
So you multiply by y.
So I multiply both sides by y. So dy dx is equal to y times this whole quantity, negative ln x sine x plus cos x over x quantity. And what is y?
Oh.
Look back at the beginning. What is y?
Arc x cosine x.
Y itself
Oh my.
is x cos x. So just change it back to x cos x.
Why do we have to change this back?
So that our answer is in terms of x and not in terms of y. You do not need to distribute. You do not need to simplify any farther. You can just leave it like that. Okay, that is called logarithmic differentiation. When nothing is constant. The process is the same every single time. Okay, let's try a couple more just for practice. Okay. Find the derivative of y equals the quantity 3x, which is variable, because 3x has the variable, and to the power square root x, which is also variable. And so we'll apply ln on both sides. So you introduce the ln around parentheses y, and then also introduce the ln around the parentheses 3x to the rad x. And every single time, the same algebraic technique. So we have two algebraic things going on here. Do the same thing to both sides. And then bring the power down to the front. And it will always produce a product. So I'll have rad x multiplied by ln of 3x. So the result will always be a product.
That's nice.
And then we differentiate. We apply those derivative rules. Differentiate. Okay, that you should be getting really, really comfortable with. Okay, so I apply the derivative of the natural log, which will always be 1 over y ln e times dy dx. And then we have the product rule on the other side. So I usually start with ln 3x multiplied by the product rule, which would then be half x to what new power? Negative 1/2, which I'll want to clean up. And then I'll add the rad x, the rad x, and then multiplied by the derivative of that logarithm, okay, which will be 1 over what? 3x, followed by ln e, followed by 3. Okay. Then we reduce and we simplify. So all of the natural log e's can simplify. And we can reduce the 3's and then figure out what's in the numerator and what's in the denominator. So I'll have 1 over y dy dx. And then both of these terms are going to have a numerator and a denominator. All right, so in the first term, what's left in the numerator? I don't think so.
Oh, sorry.
ln
Second term.
3x. You do yours the other way. Okay, and in the denominator,
2
a 2
and
and a rad x. Okay, and then in the other one, what's left in the numerator? Oops, did I reduce? I reduced the wrong thing, didn't I? Oops. Don't know. Clean that better. 3x. All right, the numerator is left with rad x, and the denominator is left with regular x. Is that reducible?
yeah. Negative or 1 over negative. Right?
1 over rad x. Okay, and then we'll multiply everything by y.
So multiply everything by 3x.
So dy dx is going to be equal to the whole thing multiplied by y. So I'll have an ln 3x over 2 rad x plus, and this is a 1 over rad x, and then just change the y to what it originally was defined to be. So that'll be quantity 3x to the rad 3x, to the rad x, excuse me, and you do not need to distribute. You don't need to simplify. Yeah, Chloe.
How did you get to 1 over rad x and rad x?
Multiplied by rad x over rad x.
This is x to the what power? Okay, and this is x to the what power? 1. And when you have, what do you do with those powers in algebra? You subtract them. So 1/2 minus 1. So that ultimately would be x to the negative 1/2, which then is 1 over rad x. Okay, so just like if you would have had x to the 3 over x to the 7, you would go 3 minus 7, which is x to the negative 4, which is 1 over x to the 4th. It's the same thing. We're just subtracting our powers. Okay, let's try one more of these, and then I'm going to show you a quotient rule one. Okay? All right. So again, everything about this is variable. The base is variable. It's a secant trig thing, and the power is variable. It's a tan thing. But it's going to be the same process. So we always apply ln first. So this would become ln quantity y, and then you'll start to get fast at it. Right? If I'm going to apply an ln, what else can I do at the same time? Move the tan to the front. So you can get quicker at it. Like, okay, I did both things at the same time. I applied an ln and I pulled the power to the front. Then we can differentiate. Okay, so that's going to give me 1 over y ln e. And Catherine, this is where you were asking, like, okay, if you're getting more confident, you can start to not put the ln e. Okay, but I just don't want you to forget it if it's a different kind of log, right? If it's a base 2, then you're going to need that. Yeah?
Is that what you've always told us to use natural logs?
Because natural log, there are no derivatives of any other logs other than natural. All right, then we do our product rule. So the natural log of secant x times the derivative of tangent, which is secant squared, plus, now it's going to get interesting right here. What's the second half of our quotient rule going to be here? What do we start, our product rule? Okay, tan x.
1 over secant x.
Okay, times 1 over secant x and ln e. And then what's the derivative of that? Secant x tan x. So that is reducible, isn't it?
Oh, so that is just tan squared.
Yeah, so this secant will reduce that secant. Now, is anything reducible in that first part? No, because one of them's in an ln and the other isn't. So our reducible, or we've got, maybe put secant squared in the front. And then times ln of secant x. The order is irrelevant, but then plus tan squared, because there are 2 of those. And eventually, what will I be multiplying that whole quantity by? Y. And what is that? Yeah, secant x to the tan x. And then that would be equal to dy dx by itself. So you can start to combine terms as you get more comfortable, and you don't have to simplify that anymore. Once you've got dy dx alone, you can be done. All right, last thing. Okay. Under normal circumstances, you might have approached this with the quotient rule. But I want you to, can you fast forward in your mind a little bit? Okay, the quotient rule starts with what? B, right? Which is fine, x cos x, times a prime, which is what?
X plus 5.
No, a prime, which is 1. Okay, then minus, and then the a part, which is x plus 5, and then you get to b prime. Okay, the d high part. Okay, so what would I need in order to do the derivative of the base? I'd have to do the product rule. So it's going to be the quotient rule with the product rule in it. Okay, which gets a little hairy. And then the denominator is going to have x cos x quantity squared. So I'm just going to propose that logarithmic differentiation is an alternate to the product rule that is a little cleaner, a little slicker. So let me just show you how that works. Okay, so we're going to do the same thing. Apply our ln. Both sides. So that would be ln y. And then ln of the quantity, x plus 5 over x cos x. Okay. All right. After we applied our ln, we used some rules that were special to logarithms. And so last time, the rule that was special to logarithms was that you can pull powers to the front. What other special log rules do we have? Christian? Subtraction. Okay. So I can do ln y equals ln of x plus 5 minus, okay, and then Christian, you want to take it? What's next?
Minus natural log of x cosine x.
Okay.
Oh, and then.
Okay, but how are x and cosine x related? What's the implied? They're multiplied, right? What other algebraic thing can you do with logarithms that are multiplied?
Use ln x plus ln.
Okay, so I can have ln y equals ln x plus 5, and then ln x plus ln cos x. Be careful, because these things are a quantity together. So what happens to the negative that was in front of them? Okay, so that would get distributed. So this is not calculus. What do we call this? Algebra. Okay? All right. So you might be going like, that's easier than the quotient rule? I don't know. Okay. But I think maybe yes, because now we differentiate. Okay, so now we want to do all the derivs. All right, what's the deriv of ln y? 1 over y dy dx. What's the derivative of ln x plus 5? 1 over x plus 5 dx dx, right? Which is going to be 1. And then minus 1 over x times dx dx, which is going to be 1. And then minus 1 over cosine x times negative sine of x. Okay. So the 1's are gone, right? The dx, 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 dx. So we'll have 1 over x plus 5 minus 1 over x. And what about the last term? It's a plus.
Sine x over cosine.
What's sine x over cosine x? Tangent.
No.
Okay? And what's around all of that? Parentheses. And what's in front of all of that? Y. And what was the original y? X plus 5 over x cos x. And that is what is equal to the derivative all by itself. And unbelievably enough, that is exactly equal to what you would get with the quotient rule. Algebraically equivalent. Okay? Algebraically equivalent. It does.